Light is something so familiar, yet so mysterious. Every second, trillions of photons cross the universe, some traveling for billions of years. But the question remains, can these particles of light exist forever? Modern physics tells us that photons are stable, but what if that's not true? What if the very light that determines how we see the universe can decay over time? If photons can change or disappear, it would change everything we know about particle physics, quantum mechanics, and cosmology. This is the paradox of the photon. Its fate may be the key to understanding the universe itself. Photons, as particles of light, are central to the functioning of the universe. Unlike other elementary particles, photons are unique in that they have no rest mass, which means they do not exist in a stationary state. They are always in motion, traveling at the speed of light, approximately 186,000 miles per second. This constant speed defines their nature. Photons are carriers of energy, unaffected by rest or inertia, making them essential to the transmission of electromagnetic force. Another crucial property of photons is their electrical neutrality. Because of this, they do not interact with charged particles through which they pass, except under special circumstances such as strong magnetic fields. These qualities, as well as their perpetual motion, allow photons to travel great distances in space, carrying information about the universe for billions of years. So as we mentioned, photons also play an important role in electromagnetic interactions, the forces that hold atoms together and enable chemical reactions. In this role, photons are much more than just carriers of visible light. The entire electromagnetic spectrum, from radio waves to gamma rays, is made up of photons. This range of energies reveals the true breadth of their influence, not only in illuminating the universe, but also in laying the foundation for technologies such as radio communications, medical imaging, and even quantum computing. Since the first telescopic observations, scientists have relied on photons to study distant objects. The light emitted or reflected by cosmic bodies provides insight into their composition, distance, and speed. It has transformed our understanding of the cosmos, from revealing the life cycle of stars to unraveling the mysteries of galaxies billions of light years distant. But beyond the visible, photons are also integral to modern quantum phenomena. However, their quantum nature only adds to the complexity of their role. As quantum objects, photons exhibit both particle-like and wave-like properties. In experiments such as the double slit or entanglement scenarios, photons challenge our classical understanding of particles. They can exist in multiple states simultaneously, be entangled over vast distances, and exhibit properties that seemingly defy common sense. This duality underlies many quantum technologies and keeps photons at the center of attention of both theoretical and applied science. The question of whether photons can exist forever touches on some of the most fundamental assumptions in physics. Current models describe photons as exceptionally stable particles that once created can travel through space for billions of years unchanged. Unlike many other particles that decay or interact over time, photons show no obvious signs of degradation. Their stability is crucial to how we observe the universe. Photons reaching us from distant galaxies have been on the road for almost the entire lifetime of the cosmos. One of the reasons photons are considered stable is that they do not have the same rest mass. Particles with mass are subject to decay, transforming with time into less energetic forms. Photons, however, being massless, do not obey the same rules. Their energy is completely determined by their wavelength, and as long as they remain isolated, there is no intrinsic mechanism that could spontaneously cause them to decay. This has led to the widespread belief that photons, once emitted, can theoretically exist indefinitely. But stability is not the same as invulnerability. Theoretical physics presents scenarios in which photons can undergo transformation under certain conditions. Quantum field theory, for example, suggests that in extreme conditions, such as near black holes or in regions with intense magnetic fields, photons can interact with other fields and particles in ways that change their fundamental nature. Under such conditions, protons can interact with quantum fluctuations, fields that permeate all of space and undergo rare transformations. One such theoretical possibility is that photons could eventually decay into lighter neutral particles, perhaps candidates for dark matter, although such scenarios require conditions we have yet to observe. Another possibility is the decay of photons controlled by hypothetical particles called axions. These small mass particles, according to the theory, interact weakly with photons, which means that in certain fields or under certain conditions, photons can gradually turn into axions. While such a decay would occur on an astronomically long timescale, well beyond the current age of the universe, it raises intriguing questions about the ultimate fate of light. Could photons eventually disappear from the universe altogether, leaving behind only the invisible remains of their presence? Some studies even suggest that the expansion of the universe itself may subtly affect the lifetime of photons. As the universe expands, the wavelength of photons shifts, losing energy in a process known as cosmological redshift. While this doesn't mean decay in the traditional sense, it shows that photons can be altered by their environment, gradually becoming less energetic over time. Whether this process can ever lead to the disappearance of photons is an open question. In general, although photons are considered stable, modern physics allows for the possibility, albeit remote, that they're not eternal. Moreover, the question of whether photons can decay or exist forever is not just a theoretical curiosity, but an active subject of experimental research. One of the main tools for investigating the stability of photons is the Large Hadron Collider. Although its primary function is to study the behavior of massive particles, the LHC can also gain insight into the behavior of massless particles, including photons, by observing high-energy interactions. In these high-energy environments, photons are generated in abundance by particle collisions, allowing scientists to observe their properties under extreme conditions. One focus of such studies is to look for any anomalies in photon behavior that might hint at instability or decay. If photons were to decay in other particles, such as hypothetical dark matter particles or axions, these events could leave noticeable traces in the collision data. So far, no such decays have been observed, supporting the idea of photon stability. However, this area remains critical to study because even the rarest decays can change our understanding of photon durability. One experimental approach that has become widespread is resonant inelastic scattering, where light particles are directed at certain materials and their scattering is measured. In recent years, this technique has been refined to test the possibility of photon decay by observing how photons interact with different quantum materials. A recent breakthrough study published in Nature by a collaboration of scientists from Columbia University, Nanjing University, Princeton, and the University of Munster has provided new insights into the behavior of photons. The study used fractional quantum Hall effect liquid, abbreviated as FQHE, a system of interacting electrons confined to two dimensions, to study what the researchers called chiral graviton modes, or CGMs. These CGMs bear a resemblance to gravitons, hypothetical particles thought to mediate the force of gravity. By observing how circularly polarized light interacts with the FQHE fluid, the team gathered evidence for the existence of these graviton-like particles, offering a tantalizing parallel to the quantum behavior expected of photons in extreme environments. The significance of this experiment is the use of polarized light to detect subtle changes in the spin of photons as they interact with a material. This interaction is key in determining whether photons undergo any transformation or decay under certain conditions. The results, although focused on the CGM, provide a template for testing the stability of photons in other high-energy or quantum field environments. By extending this method to more extreme environments, scientists hope to see the first glimpse of photon decay, if it exists. Although such experiments are breaking new ground, evidence of photon decay is still lacking. However, each new advance in detection techniques opens up more and more possibilities to reveal their true nature. Since we've touched upon quantum electrodynamics, or QED, let's delve a little deeper into it. QED is based on the photon, the carrier of the electromagnetic force. According to this theory, photons mediate interactions between charged particles such as electrons and protons, allowing them to affect each other without physical contact. QED, one of the most accurate theories in physics, describes how these particles exchange photons, transmitting an electromagnetic force that governs everything from atomic structures to the behavior of light itself. When two charged particles come close together, they exchange virtual photons. Photons that exist for only a short time and do not carry energy in the traditional sense. These virtual photons transfer momentum between the particles, resulting in either attraction or repulsion depending on their charges. This process constantly occurs at the quantum level, invisible to our senses, but fundamental to all interactions involving charged particles. In fact, the very structure of atoms, and thus of matter, depends on photons holding electrons on nuclei. However, the role of photons in QED goes far beyond basic electromagnetic interactions. Photons are also involved in some of the most counterintuitive phenomena in quantum mechanics. For example, in the phenomenon of quantum entanglement, two photons can be coupled in such a way that the state of them instantly determines the state of the other, even if they're light years apart. This bizarre coupling defies classical explanation, illustrating the non-local nature of quantum reality. Entangled photons remain correlated no matter how far apart they are. This discovery has profound implications for quantum information and communication technologies. Another key phenomenon associated with photons is quantum superposition, where a photon can exist in multiple states simultaneously. In such a state, a photon does not simply follow a single path or have a single polarization, but can occupy several variations at the same time. This concept was famously demonstrated in double-slit experiments, where a single photon can interfere with itself, as if it had passed through both slits simultaneously. The results of such experiments challenge our classical understanding of particles and waves by illustrating the probabilistic nature of quantum mechanics. What makes photons particularly interesting in the context of quantum mechanics is their very massless nature. As we've already mentioned, photons are considered fundamental particles that have no rest mass, which distinguishes them from almost all other known particles. According to quantum theory, massless particles should move at the speed of light. This property is very important because thanks to it, photons can instantly transmit electromagnetic forces through space while respecting the rules of the special theory of relativity, which prohibits any massive particle to reach the speed of light. This massless nature also explains why photons are not subject to the same decay processes as other particles. In QED, photons can be created or absorbed, but never lose energy over time unless they interact with other fields or particles. This energy depends directly on the frequency of the photon, with higher frequency photons, such as gamma rays, carrying more energy than lower frequency photons, such as radio waves. Nevertheless, regardless of frequency, all photons share the common feature of being massless, which ensures their stability in time and space. Theoretical models of photon interactions in turn consider exciting possibilities where photons can transform into other particles under extreme conditions. One of the most compelling predictions involves the interaction of photons with strong electromagnetic fields. Under such conditions, photons can transform for an instant into particle-antiparticle pairs, a phenomenon known as photon splitting or pair production. This process, often discussed in the context of quantum electrodynamics, predicts that photons can transform into electron-positron pairs in the presence of fields so strong that they distort the vacuum itself. Such interactions are rare and usually occur only near highly charged objects, such as around neutron stars or in high-energy particle colliders. These transformations do not lead to the photon decay, but rather emphasize the duality of the photon behavior under the action of extreme forces. One of the best studied cases of photon interactions occurs in the presence of magnetic fields on the scale of billions of Tesla, such as in magnetars, a type of neutron star. Extreme conditions near these stars can cause photons to be converted into electrons and positrons, allowing scientists to study such interactions indirectly by observing the emissions from these objects. But let us return to the presentation of the question on a global scale. And first of all, of course, we turn our attention to the phenomenon of cosmological redshift, one of the most striking evidences of the existence of an expanding universe. As the universe expands over time, the space between galaxies increases, and as photons pass through this expanding space, their wavelengths are stretched along with the space. This stretching causes light to shift to the red part of the spectrum, the very phenomenon known as redshift. Cosmological redshift is directly related to the theory of an expanding universe, first proposed by Edwin Hubble's observations of galaxies moving away from us. The farther away a galaxy is from us, the greater the redshift of its light, which is a clear signal that the universe itself is expanding. This shift not only affects the light we see from distant galaxies, but also directly the photons emitted immediately after the Big Bang, which form the cosmic microwave background. The CMB represents photons that were released about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to escape from the dense plasma. These photons, they give a glimpse of the early universe. Their uniform redshift tells us not only about the conditions at that time, but also about the rate of expansion over billions of years. It was the study of CMBs that allowed astronomers to confirm the Big Bang theory and gain insight into the composition of the universe. These photons revealed patterns that have subsequently helped shape our understanding of cosmology. Without them, many aspects of the Big Bang theory would remain unproven. So, over billions of years, as protons travel through space, redshift gradually reduces their energy. Light emitted as high-energy gamma rays or ultraviolet waves can only reach us as radio waves or infrared radiation. Photons play a central role in almost every major discovery in cosmology, from mapping the large-scale structure of the universe to the discovery of exoplanets. The light that reaches us carries fundamental information essential to the study of the cosmos. One of the most intriguing aspects of photon research today is their potential role in solving some of cosmology's biggest mysteries, such as dark matter and dark energy. Although photons do not directly interact with dark matter, they help us trace its presence through gravitational lensing. When light bends around massive objects, this bending reveals otherwise invisible mass in the universe, allowing us to map the distribution of dark matter in space. Meanwhile, redshift studies of distant supernovae have provided important evidence for the existence of dark energy. Photons from these distant explosions show that the universe is expanding faster now than it was billions of years ago, indicating the influence of dark energy. Whether we're studying the nature of dark energy, mapping dark matter, or confirming the details of the Big Bang, these little guys remain our most important tool in unraveling the deepest secrets of the universe. However, alternative theories suggest that photons might not be as fundamental as we previously thought. Rather than being the indivisible particles underlying quantum mechanics, they may arise from deeper processes underlying the universe. One such idea suggests that photons may be the result of interactions in the quantum field, or even a byproduct of space-time itself. This viewpoint changes our perspective by suggesting that photons may arise from complex layers of physical laws beyond the standard model. Among the more radical theories is the holographic principle. According to this concept, all information contained in three-dimensional space, including photons passing through it, can actually be encoded on a distant two-dimensional boundary. From this point of view, photons may exist not as independent entities, but as emergent properties of this holographic structure. Their behavior in our universe would be a projection of deeper processes occurring in this two-dimensional structure. If photons are not eternal or part of a deeper structure, such a discovery will force us to rethink some of our most basic assumptions about reality. The very concept of light, central to everything from particle physics to cosmology, would be reconsidered. Understanding the different nature of photons could challenge long-held ideas about the nature of matter, energy, and even space-time. As we delve deeper into the mysteries of physics, one thing is clear. Reality may be far stranger than we ever imagined. So stay tuned as we continue to explore the frontiers of science, unraveling the universe, one discovery at a time. solar system is unique because of its special structure and, most importantly, optimal conditions for life to develop. Therefore, missions that are aimed at finding planets we could potentially inhabit and trying to find them in similar star systems. But what if we tell you there is a planetary system not far from us that is very similar to ours? And more to that, it consists largely of planets that are similar to Earth. Today we'll tell you about the TRAPPIST-1 system and whether or not its planets would be able to support life. The TRAPPIST-1 system was discovered very recently. In 2016, a team of scientists led by Michael Guillon and Susan Lederer discovered 3 planets orbiting an ultra-cool dwarf star known as TRAPPIST-1a, 40 light-years, 235 trillion miles, 378 trillion kilometers from Earth. However, the very next year, NASA astronomers made a new discovery using the Spitzer Space Telescope. Turned out there are as many as 7 planets in this planetary system. However, TRAPPIST-1 has no gas giants like Saturn or Jupiter. Almost all of its planets are structurally similar to Earth. These findings led scientists to speculate that perhaps TRAPPIST-1 may have the potential for life to exist there. What does the TRAPPIST-1 system look like? The central star, as we've already mentioned, is a red dwarf. It has 7 planets revolving around it, roughly the size of Earth. All of them have the name TRAPPIST-1, but each planet has an individually assigned alphabetical index from TRAPPIST-1b to H. Unlike our solar system, TRAPPIST-1 has several other important distinguishing features. First, all the planets in this system only face the parent star with one side, the same way as we see the moon. The time it takes the planets to rotate around their axis is the same amount of time it takes them to orbit the star, which means that one day on these planets is equal to 1 year in length. This process is called tidal locking. It's caused by the gravitational interaction between space objects. Secondly, all the planets are very close to each other. It is likely that the desensification of the system is caused by an internal migration of the planets, which also led to their resonance. For example, the distance between the star and its nearest planet, TRAPPIST-1b, is only 11 million miles. For reference, the average distance between the Sun and Mercury is 36 million miles. This means that these planets might be heated better due to relative proximity to their star, as well as interplanetary gravity, which would allow them to retain water inside themselves. Does this figure that all these planets can hypothetically be habitable? Let's try to figure this out. First, let's take a closer look at the central star. TRAPPIST-1a is very cold and small when compared to our Sun, for example. Its surface temperature is only about 4,154 degrees Fahrenheit, whereas the temperature of the Sun is close to 9,930 degrees Fahrenheit. Its size can be compared with Jupiter and its mass approximately 13 times smaller than the Sun's mass. However, red dwarfs burn their hydrogen supply much more slowly, which means they can exist for a very long time, several trillion years, in contrast to the age of stars like the Sun, which is closer to 10 billion. According to research by Adam Bergesser of the University of California, TRAPPIST-1a may be about 7.5 billion years old, which would be considered a relatively young age for such stars. However, if red dwarfs are so cold, how could they heat the entire planetary systems? True, for a long time there was an assumption that red dwarfs were not capable of supporting life, but the discovery of TRAPPIST-1 has changed scientists' view. The peculiarity of the proximity between the planets and the temperature of the star maintain, on average, moderate temperatures in the range from negative 171 degrees Fahrenheit to 258 degrees Fahrenheit on these planets. Now, what's more, thanks to relatively low temperatures as far as stars go, dwarfs can help conserve water on the planet in their planetary system, even the ones closest to it, and also, interestingly, funnel amino acids and important chemicals through their flares. On the other hand, dwarfs can expose nearby planets to strong UV radiation, creating conditions unsuitable for life. Therefore, let's move on to the planets themselves now and find out how the characteristics of their system affect them and the potential life on them. The first on the list is TRAPPIST-1b. Its radius is 10 times larger than the radius of Earth. Similar to Earth, it's also made of rock, iron, and likely ice. Interestingly, 1b may even contain a small layer of water, about 0.2% of its total mass. Although some scientists are inclined to believe that the planet is completely dry and has only oceans of magma. However, the conditions on this planet are far from earthly. Obviously, the proximity to the parent star must result in a very heated surface. Moreover, the gravitational influence from the star may cause strong volcanic activity, heating the surface even more and melting the internal rocks. However, the temperature on 1b is too high even for this. Temperature there reaches 2,156 degrees Fahrenheit, which is 2.5 times higher than on Venus at 860 degrees Fahrenheit. The reason for such temperatures may be the high density and possibly atmosphere in which gas accumulates after volcanic eruptions, which prevents heat from leaving the planet. The next planet, TRAPPIST-1c, is similar in composition to TRAPPIST-1b, but most likely has neither ice nor water. It is the heaviest planet in the entire system, even though it has a smaller radius than 1b. It's also very likely that it has high levels of activity. That's due to the influence of the star and orbital resonance. The exact surface temperature of 1c, it's unknown. The star can heat it up to about 158 degrees Fahrenheit, but the internal activity of the planet is capable of raising the temperature several hundred degrees. However, it will most likely not reach the same temperatures as 1b due to the atmosphere, which is likely less dense. One of the features of 1c is its massive core made of metal, which is almost 1.5 times larger than Earth's. Because of this, its large magnetic field is able to protect the planet from stellar wind, a stream of charged particles that could destroy the atmosphere. However, 1c is unlikely to contain water, and like 1b, the surface heats up significantly due to gases, which makes life on these planets impossible. Next, we have TRAPPIST-1d, one of the smallest planets in the system, with a mass about 3 times smaller than Earth. It's composed of rock and metal, but very likely, like 1b, it must have an ocean, a layer of ice, or a dense atmosphere. And that's according to the theoretical research of its mass and radius. Astronomer Vera Dobos believes that the surface on 1d could be as reflective as the surface of Earth. This means that 1d may have liquid water and a dense atmosphere, which in turn may even contain ozone, which would protect the planet against harmful radiation. Moreover, the scientist also suggests that unlike 1b and 1c, 1d can avoid a mass-scale greenhouse effect, which would greatly increase surface temperatures due to this small mass. However, despite strong evidence, some scientists have other assumptions about the possibility of life on TRAPPIST-1d. Researchers from the University of Washington believe that 1d receives more energy from the star than the more distant planets, and therefore it may be similar to our Venus with a pronounced greenhouse effect like on 1b or 1c. Therefore, life is unlikely to develop there. On the other hand, it may also have some hydrogen in the atmosphere, which would prevent it from overheating. Furthermore, its atmosphere may contain a very little CO2, which would have a negative effect on the emergence of life. In addition, its orbit is almost circular, as in 1d may be heated slightly due to gravity. Finally, due to its small size, the planet may not have a magnetic field. Therefore, the stellar wind could carry away volatile particles from the atmosphere, including water, as it may have happened with Mars. The conditions on 1d are quite controversial, so it requires further research from scientists. But the fourth planet in the TRAPPIST-1 system presents the greatest interest to the scientific world. TRAPPIST-1e is more similar to Earth than other planets in the terms of radius, density, and heat received from the central star. Its orbit is 2.7 million miles away from the star, which results in the planet completing a full revolution in 6 days. Its composition as a whole is very similar to that of 1C. 1E is mainly composed of rock and metal. Does that mean there's no water there, like on 1C? NASA researchers believe that 1E is in a so-called habitable zone, a distance within a planetary system where it's neither too warm nor too cold, which also keeps water in its liquid form. Therefore, it's very likely that 1E may contain water, and in quite large quantities, in fact. Researcher Vera Dobos suggests that an excessive greenhouse effect may not be characteristic for this planet, unlike all the previous planets we've discussed so far. This means that 1E would be able to maintain a moderate temperature, maintaining entire oceans on its surface. Moreover, due to its weight, 1E may have an atmosphere that's not too dense. A group of scientists led by astrophysicist Martin Turbet believes that the atmosphere on 1E may be rich in CO2 and contain almost no hydrogen, preventing the planet from overheating. Additionally, 1E can retain its atmosphere for an extended time despite the impact of the stellar wind, and may therefore create optimal conditions for life. However, the exact mass of 1E has not yet been established. Therefore, just as with 1D, it's difficult to say for sure whether or not there may be water on it. Although scientists largely agree on the presence of an ocean and the planet's potential habitability, some suggest that it may be a homogeneous rocky planet. The following planets, TRAPPIST-1F and 1G, are also presumed to be generally similar in their mass, rocky structure, radius, and density to planet 1E. However, that's where the similarities end. Both planets are at a great distance from the star, one 3.6 million miles away, and the other is 4.3 million miles from the parent star, respectively, also within the habitable zone. However, their surface is not as heated by the red dwarf, and scientists suggest that both of them may be covered with a solid layer of ice. Nonetheless, they may have the same heating potential as 1D from gravitational interaction with the star. That is, despite the very little heat from the star itself, planets can be heated properly from the inside, and therefore they are likely to have a global ocean under the ice. Furthermore, likely due to their high internal temperature, the water on these planets could evaporate, forming a dense atmosphere rich in oxygen. And so it is possible that their surface may not be that cold, but could even be warmer than Earth's. However, according to research by a group of scientists led by Bill Quarles, up to 20% of 1F is made of water. Given its possible internal heating as well as the mass of the planet, likely smaller than that of Earth, scientists believe that water can only exist there in the form of clouds. Equally, 1G also evolved with a lot of water. According to some scientific reports, the depth of its ocean can be 416 miles. Although such ample amounts of water may seem beneficial to life, oceanic evaporation can significantly increase the oxygen pressure in the atmosphere, casting doubt on the possibility of any development of a living organism. Therefore, despite the likely presence of water, the question of the habitability of these planets requires new research focused on their atmosphere. And finally, the seventh planet, TRAPPIST-1H, is the most removed from the star as well as the smallest in the entire system. Unlike all the other planets, 1H may be composed almost entirely of water and is likely to have very little rock in its composition. However, it's likely also that 1H is heated much less than the others. The parent star alone would bring the surface temperature to only about negative 153 degrees Fahrenheit. Furthermore, some scientists suggest that the amount of heat generated by gravity would also be quite low for 1H. However, researcher Kathleen Mant believes that 1H may have a lot of volcanic activity, spewing water instead of lava. That would mean the planet's able to replenish its atmosphere due to the emitted gases. Additionally, the remoteness of 1H allows it to firmly retain its atmosphere, probably consisting of nitrogen and methane like on Titan, since the stellar wind hardly touches it. And yet even this quality does not speak in favor of life on the planet. It's still very cold and therefore probably cannot sustain water in liquid form. But the question remains, could life hypothetically exist in this TRAPPIST-1 system? The tidal lock is not great for sustaining life because one side of the planet's always scorchingly hot and the other side is freezing cold. However, almost all planets in the system can cope with this drastic difference in temperature due to their water content and their atmosphere. The heated ocean and atmosphere can transfer heat to the colder zones, maintaining the temperature balance. Nonetheless, only the middle planets, 1D and 1E, meet the criteria to be on the list of potentially habitable planets. 1B and 1C are too hot, may have lost water due to their gravitational relationship with the star, whereas 1F and 1G and 1H are probably not warm enough due to the weak greenhouse effect, or they're also quite hot. But however, 1D and 1E still require extensive research, since conditions on these planets may turn out to be more similar to Venus, although 1E is very unlikely to fall into that category. In fact, if both planets were covered in ice, they might still be habitable. The TRAPPIST-1 system remains very interesting to all of us. In 2021, NASA sent the James Webb Telescope to the L2 Lagrange point with a view to study TRAPPIST-1 among other things. Therefore, we can expect new data on a distant system very soon, which would reveal more secrets about the origin of our universe and possibly even the origin of life. More than once, you've caught yourself wondering what will happen in the future, in 100, 1,000, or even in 1,000,000 years. And for you, we tried to look behind the screen of the future through the evolution of the stars we see in the sky every night to absolute oblivion. Today, we'll try to tame time and find out what our universe will look like in 100 million years. Check your seatbelts. In a few seconds, you'll find yourself at the very beginning of the universe's life and travel all the way to its last moments. We're about to begin. Of course, nothing in our universe can exist forever. In 100 million years, all the massive stars that we see every night will disappear, leaving only fields of nebula. Stars start out as large molecular clouds of gas and dust. They evolve over tens of millions of years and then remain shining in space for millions or billions of years. Stars in particular, although they hardly change during their lifetime, eventually, due to the synthesis of hydrogen to form helium, their temperature and brightness decrease and their core shrinks. The death stage begins, lasting slightly less than their actual life. Then stars with a mass close to the sun in about 9 to 10 billion years become red giants. After billions more years, they completely fade away, leaving behind only remnants in the form of white dwarfs and a plume of gas and dust from which new stars are born. However, the period of 100 million years will also affect our sun. It will become brighter and warmer by 1%. In 1 to 2 billion years, the sun will heat up to a point that's fatal. But what if this process could be slowed down? Still, a period of 100 million years is incredibly long for humanity. During this time, our science will be able to reach a level that may seem like science fiction to us now. In 100 million years, we'll probably be able to tame the stars and determine how much longer they'll shine thanks to stellar engineering. During this period of time, humanity will hypothetically be able to replenish the star's fuel reserves or artificially influence its nuclear reactions. Then, the sun could survive longer and not threaten life on the planet. Manipulation of stars is also likely to create conditions for the development of life on planets that are not currently considered habitable. In particular, The humanity of the future will be able to extract hydrogen and helium from stars for energy production. Human civilization will grow to an incredible scale, so the resources offered by the planets alone may not be enough to supply energy to such a large number of people. Furthermore, fuel extraction using the theoretical Dyson sphere, which would harvest stellar energy in close proximity to a star, would preserve resources and the environment on the planets where people would hypothetically live. On the other hand, what if stellar engineering allows us to accelerate their aging by collecting fuel? In this case, life near these stars will be dangerous, and the galaxies in which these stars are located will begin to age rapidly. Yes, not only stars are affected by the passage of time, galaxies, and in particular the one we live in, appeared at the beginning of the formation of the universe and continues to move towards oblivion. However, before they die, galaxies, like stars, will go through a long way of evolution, but by merging with others. Over a long period, smaller galaxies will become part of larger ones. So in 100 million years, the number of small galaxies will likely decrease, as well as the mixture of spiral and elliptical galaxies will increase slightly. The humanity of the future will see repeated examples of galaxy mergers, especially with small galaxies, which can lead to the formation of new structures, such as wave tails and, in particular, supermassive black holes. The Milky Way is also moving towards another galaxy, Andromeda. Although we shouldn't worry, even in millions of years, their collision would take place in about 5 billion years. In 100 million years, our galaxy will have traveled about 978,000 light years, although this will not affect us in any way. After the same amount of time, the galaxies will change their location, moving to areas with different densities that will affect their morphology and star formation in different ways. But in the future, bright, beautiful galaxies will also fade away. The reason for this is the death of stars, especially massive ones, which determine the color and brightness of galaxies. After the last explosion of a star, most of its gas will remain inside the galaxy, keeping it alive, but some of it will leave the galaxy. Because of this, fewer large stars are formed. The mass of the galaxy suffers, and in millions of years there will probably only be a black hole in its place. In fact, it isn't possible to find anything static in our universe. Absolutely everything is in motion, including perhaps the universe itself. From the very beginning, the Big Bang, the universe has never stopped expanding. In the early stages of the hot Big Bang phase, the universe expanded faster than light. Only after cooling down, when the energy density of matter became higher and protons, neutrons, and electrons were formed, did the speed slow down a bit. And in 5 billion years, it slowed down a lot. However, both now and in the future, the universe will not stop expanding. It should be understood that expansion does not mean that matter is moving, but that time itself is expanding. Like a balloon with 2 dots drawn on it, the more you inflate it, the further apart the dots will be. However, this hardly affects objects that are connected by gravity, like our galaxy and Andromeda, or even ourselves. The amount of ordinary and dark matter always remains constant. Only space and density of matter change due to its spread over a large volume. However, we can see that other galaxies are moving away from us. In 100 million years, the galaxies of the local group may be so far away that it will be a little harder for us to see them. While faraway clusters of galaxies like CLJ 1001 plus O220 will probably be almost invisible. However, the expansion of the universe is accelerating. The rate of expansion is 44 miles per hour, which means that every 3.26 million light years, the speed increases. This will not end well for the universe. In millions of years, it would be harder for cosmic bodies to form. The building blocks would fly apart too quickly. The main factor in this is dark energy, because hypothetically, it can counteract the gravity of matter. Dark energy is a hypothetical energy and a necessary property of time that can lead to inevitable consequences in the future. So in 100 million years, the expansion rate may increase so much that galaxies would stop merging and thus evolve. The mass of dust and gas that's ejected after the death of stars will be dispersed. Stars will form less often. Moreover, in billions of years, gas leakage may become too fast. In this case, absolutely nothing will be able to form. No stars, no galaxies, no life. The heat death will eventually come. The heat death is not related to the transformation of our universe into hell through the evolution of stars. The scenario of the future fate of the universe is based on the second law of thermodynamics, according to which, in a closed system, entropy, or the state of disorder, increases over time. That is, the energy will dissipate in such a way that absolutely nothing will be able to form into something unified. You can think of it as heat energy leaving your cup of tea and dissipating in the room. Eventually, the temperature of the tea becomes the same as the room, so you can no longer get warm when you drink it. So the drink is not doing its job. So galaxies will be too far apart and stars will start to fade because there'll be no more necessary inflow of energy or matter for the evolution of stars, planets, or other space objects. The universe will become completely dark and empty. Dark energy may threaten not only heat death in the future. If the expansion becomes many times faster over the next 100 million years, then the universe can expect absolute death in the future. Stars will not just stop forming as in the previous scenario. Nothing will exist, not even fundamental particles. Since matter, such as stars, remain unchanged, they don't increase their mass through expansion. Then, when in a few billion years the expansion can become immeasurably fast, the stars will not withstand such an influx of energy and will simply explode. Another scenario for the end of our existence is the Big Rip. It suggests that since the acceleration of expansion probably cannot be influenced, in 200 billion years it will become so fast that gravitational interaction will be broken. Planets will leave their orbits, and subsequently the electromagnetic force that maintains the integrity of stars will not be able to resist dark energy. With even more time, even atoms will not be able to resist, and they'll be torn apart. Moreover, there's a possibility that after the Big Bang, everything in the universe will return to the first stages of the Big Bang. However, what will remain in the singularity will not look like the plasma that was at the beginning of the Big Bang itself. It'll be cold and dilute, as opposed to hot and dense. That is, no matter how terrible the hypothetical end of the universe may be, there is a chance that this end will be a new beginning. Another danger to the entire universe may be hidden in ourselves. We all know that everything around us is made of atoms. There are two elementary particles in the nucleus of an atom, a proton and a neutron. We also know that these particles are stable within the nucleus, meaning they cannot decay. But what if this is not necessarily true? The proton is one of the most common particles in the universe. It can exist even outside the nucleus. The proton has reasons to be stable, namely the laws of conservation of energy, charge, and baryon number. Although according to the standard model of physics, the proton cannot decay in any way. The latest theories, such as the theory of grand unification, which combines the three fundamental forces, electromagnetism, weak and strong interactions into one, allow it. So, in the distant future, there's a possibility that this particle will decay. This seemingly unlikely process is unlikely to cause disaster to the entire universe. But if it happens on a massive scale, then in millions or even billions of years, part of the universe will cease to exist. The proton decay will destabilize the nucleus of atoms and produce decay products that can affect the entire structure of the universe as matter begins to decay. But the whole world will not disappear. The entire system of galactic evolution in the regions where proton decay occurred would be disrupted. The people of the future can exhale. The protons in their bodies are likely to decay. But the 100 million year time frame may bring another threat in addition to the heat death and the Big Bang. If the collapse of protons is too large and strong, it will trigger an inevitable scenario of the terrible end of the universe, but not because of protons alone. The destruction of all matter in the universe, without even a hint of its former existence, is hypothetically possible through a bubble. You've probably heard of the Higgs boson, which is a fundamental component of the Higgs field, a theoretical field that permeates the entire universe, and to which particles gain mass when they interact with it. In addition, the Higgs field can affect the vacuum. We are used to thinking that a vacuum is an empty space, but there are quantum fields in it, so a vacuum simply contains as little energy as possible. So, the field determines whether the universe is in a true vacuum or a false vacuum. A true vacuum means the universe is stable and has the lowest possible vacuum energy state. A false vacuum, on the other hand, means the universe is metastable, meaning with a higher energy but less stability. According to modern theoretical data, our universe is metastable. This is precisely the threat to all future life and matter. If in 100 million years an event occurs in the universe that would have enormous energy, such as a massive proton decay, then a small particle of the universe will hypothetically be able to enter a state of true vacuum. Thus, a bubble of true vacuum will form, which would expand at the speed of light, destroying all matter and fundamental particles in its path. Life can hardly appear in any form after such an intervention. The universe as we know it will change over time and one day become completely unknown to us. It will continue to evolve, but like all of us, it will begin to fade away at some point. We don't know when this will happen. No matter how hard we try to look into the future, we'll never get an accurate prediction. One thing we can say for sure about the future is that humanity will see more than one outstanding discovery, which perhaps in 100 million years will reveal the full history of the universe and ourselves to the humanity of the future. The vast expanse of space, where stars are born and galaxies collide, there is a phenomenon so elusive that it has been dubbed the ghost of the universe. It is not about spirits and not a figment of one's imagination, but about ripples in the very fabric of space-time, gravitational waves. Albert Einstein first predicted their existence more than a century ago, but it wasn't until 2015 that humanity was finally able to detect them. Yet these waves are not just a cosmic whisper, they are the universe's way of telling its own story, a story we are only beginning to decipher. Imagine a celestial body so dense that just a teaspoon of its material would weigh billions of tons. These are pulsars, remnants of exploded stars that serve as cosmic clocks with unprecedented precision. Scientists use these cosmic chronometers scattered throughout our galaxy to listen to the ghostly murmurings of the universe. The universe has a story to tell, and it's time to listen. According to Jocelyn Bell Burnell, gravitational wave astronomy will be the astronomy of the 21st century. But what are these elusive gravitational waves, and why have they so captured the minds of scientists and stargazers? Gravitational waves were first predicted by Albert Einstein in 1915 and is part of his general theory of relativity. For decades, they remained a mathematical curiosity, a byproduct of equations describing the distortion of space-time by massive objects. Imagine that you're throwing a stone into a pond. The stone disturbs the water, creating ripples that spread around. Similarly, when massive celestial bodies such as black holes or neutron stars interact, they disturb the fabric of space-time by sending ripples, gravitational waves that spread through the universe. It wasn't until a century after Einstein's prediction that we had the technology to detect these ripples. In 2015, LIGO, the Laser Interferometer Gravitational Wave Observatory, made a groundbreaking announcement. They had detected gravitational waves from the collision of two black holes, confirming Einstein's theory and opening a new window to space. But detecting these waves is no small task. As Professor Kip Thorne notes, the stretching and compression of space by a gravitational wave is so slight that it is staggering. That's where pulsars come into play, but more on that later. Why are gravitational waves so important? They offer us the opportunity to observe cosmic events that would otherwise be invisible. They can provide insight into the behavior of black holes, the nature of neutron stars, and even the early moments of the universe. As we delve into this new area of astronomy, we are not just using telescopes that capture light. We are using the entire galaxy as a gravitational wave detector. So imagine a celestial object so dense that it packs the mass of our sun into a sphere only a few miles in diameter. These mysterious objects are known as pulsars and are the most accurate timekeepers in the universe. Pulsars, discovered in 1967 by Jocelyn Bell Burnell and Anthony Hewish, are the remnants of massive stars that exploded as supernovae. What remains is a highly magnetized rotating core emitting beams of electromagnetic radiation. As Dr. Maura McLaughlin states, pulsars are incredibly stable rotators. Their predictability is comparable to an atomic clock. Indeed, the stability of pulsars is remarkable. Some pulsars rotate hundreds of times per second, and their rotation period can be predicted with remarkable accuracy, making them ideal cosmic clocks. Scientists have harnessed the power of this cosmic clock amazingly. By observing an array of pulsars scattered across our galaxy, they've created what is known as the Pulsar Synchronization System, or PTA. This array serves as a highly sensitive detector of gravitational waves. As gravitational waves travel through space, they cause tiny but noticeable fluctuations in the timing of pulsar signals. It is these fluctuations that scientists are looking for when trying to detect elusive gravitational waves. According to Dr. Xavier Siemens, the pulsar timing method is the only way to detect low-frequency gravitational waves. The precision required for this kind of work is staggering. We are talking about measuring pulsar synchronization changes to within a few hundred nanoseconds. It's like trying to measure the thickness of a sheet of paper at the distance from the Earth to the Moon. So as we've learned, pulsars are not just fascinating objects. They are essential tools in our quest to understand the universe. They serve as beacons in the dark reaches of space, guiding scientists into the uncharted waters of gravitational wave astronomy. Nanograv is a consortium of scientists and engineers founded in 2007, dedicated to the ambitious task of detecting gravitational waves using pulsars. As Dr. Andrea Lahman puts it, we're not just looking at the universe, we're listening to it. Two key players in this endeavor are the Arecibo Observatory in Puerto Rico and the Green Bank Telescope in West Virginia. These are not just ordinary telescopes. They are ears attuned to the symphony of the cosmos. Nanograv uses what is known as the Pulsar Timing Array, or PTA. This array uses precise synchronization of signals from multiple pulsars to detect tiny distortions caused by the passage of gravitational waves. It's like a cosmic spider web, where each thread is a pulsar and the spider at the center is our telescope system. In 2020, nanograv hit the headlines with data hinting at the possible detection of a gravitational wave background. While this was not a definitive detection, it was a tantalizing sign that we were on the right track. Dr. Joseph Simon described it as a strong hint of a long-awaited signal. The work of Nanogram is not the effort of one person or group of people. It's part of a global network of scientists and observatories working together to unlock the deepest mysteries of the universe. Collaboration is key, and as Dr. Maura McLaughlin notes, the more pulsars we can add to our array and the more we can collaborate internationally, the stronger our detection capabilities will become. Imagine using the entire galaxy as a scientific tool. It sounds like the idea of a science fiction novel, but that's exactly what astronomers do when they use pulsars to detect gravitational waves. The galaxy becomes a colossal, finely tuned detector, operating on scale beyond imagination. Each pulsar in our galaxy can be viewed as a single data point in this grand experiment. But as we discussed earlier, it is not just any data point. It is a very precise clock that ticks with astonishing regularity. Traditional telescopes allow us to see the universe in various forms of light, but when we use the pulsar scattered throughout our galaxy, we don't just see, we feel ripples in space-time. It's a completely different way of observing the universe. When a gravitational wave passes through a galaxy, it causes small changes in the timing of pulsar signals. These changes are incredibly subtle, often lasting only a few hundred nanoseconds. However, when you're dealing with precise objects like pulsars, even such tiny variations become significant. Detecting these changes requires an extraordinary level of precision and a deep understanding of the various factors that can affect pulsar synchronization. Everything from interstellar gas to the pulsar's own magnetic field can introduce noise into the data. Separating this noise from the potential gravitational wave signal is a monumental task. The beauty of using a galaxy-sized detector is that it allows scientists to study gravitational waves of much lower frequencies than ground-based detectors such as LIGO or Virgo can. These low-frequency waves may hold the key to understanding supermassive black hole mergers and other large-scale cosmic events. By turning our galaxy into a colossal scientific instrument, we're not just pushing the boundaries of what's possible in observational astronomy. We're redefining our understanding of the cosmos. In the field of science, some discoveries simply add footnotes to existing textbooks, and some require a complete rewrite. The results of Nanograv 2023 fall into the latter category. These are not just incremental updates. These are seismic shifts in our understanding of the universe. Earlier this year, Nanograv Collaboration made an announcement that caused a wave of excitement in the scientific community. After years of careful observations and data analysis, they presented evidence of a persistent gravitational wave background. As Dr. Joseph Simon remarked, this is the moment we've been waiting for. The background of gravitational waves is akin to a cosmic symphony, a continuous hum of low-frequency gravitational waves filling the universe. Unlike loud and isolated events such as black hole mergers, this background is a subtle, ubiquitous signal. It is the white noise of the cosmos, and detecting it is a monumental achievement. The implications of this discovery are profound. The background of gravitational waves may provide clues to the events that occurred shortly after the Big Bang. It may also shed light on the mysterious dark matter and dark energy that make up much of the universe. The 2023 results also have implications for theoretical physics. They serve as a rigorous test of the general theory of relativity and could potentially reveal deviations that point to new physics. This is a tantalizing prospect that excites theorists and experimentalists alike. The public reaction to the results of Nanograv 2023 study has been one of awe and wonder. It's a testament to science's ability to capture the imagination and evoke a sense of collective curiosity, reminding us that the universe is far more complex and fascinating than we ever dared to imagine. As we stand on the threshold of new discoveries, it's natural to wonder what the future holds for gravitational wave research. Future advances in technology will undoubtedly lead to more sensitive detectors capable of picking up even fainter signals from space. Imagine telescopes not only on Earth, but strategically placed throughout our solar system, working in unison to create a system-wide pulsar timing array. New materials and computational methods are also on the horizon. These could greatly reduce the noise in our measurements, making it easier to detect gravitational waves and understand their properties. As we improve our instruments, our window on the universe is expanding. And speaking of pulsars, it's impossible not to mention the cover of Joy Division's iconic Unknown Pleasures album. This iconic black and white graphic features 80 wavy lines, each representing the signal from pulsar B1919+21, the first pulsar ever discovered. To mark the 40th anniversary of the record, researchers from the Jodrell Bank Observatory at the University of Manchester revisited this very pulsar a few years ago. They recorded its signals using a radio telescope located just 14 miles from the studio where the album was recorded. The cover image, seemingly chaotic at first glance, on closer inspection actually reveals some order. This star still continues to be the subject of intense research to this day. Interestingly, the signal of pulsar B1919+21 has remained remarkably constant over the years. Recent observations from the University of Manchester's Jodrell Bank Observatory show that the pulsar continues to emit its characteristic radio waves just as it did 4 decades ago. Can gravitational waves help us understand the mysterious dark matter and dark energy? Can they provide insight into the early moments of the universe, the moments after the Big Bang? The possibilities are as limitless as the universe itself. As we look into the future, one thing is clear. Gravitational wave research is not a passing trend. It is a growing field that could revolutionize our understanding of the cosmos. It is a journey of discovery that we are just beginning. And the road ahead is long, winding, and full of wonders yet to be discovered.